Teaching math and science in lower secondary school offers a unique opportunity to help achieve educational goals across several disciplines. Compulsory schooling focus should be put on those disciplines to form a sound base of scientific education, but too often they just get condensed in definitions and dogmatism that distance and frustrate students. The project from the study of the chemical solution to the mathematical concept of ratio stems from my previous teaching experience as well as from a need to experiment teaching and learning methods based on an interdisciplinary approach and attention to both communication and student motivation. The project moves around the study of a water dissolution of solid substances for which I knew I could run simple lab experiments that would easily relate to the students' everyday life experience. However, the definition of concentration would inevitably imply mastering the mathematical concept of ratio. Hence, the interdisciplinary aspect of the project, where different scientific disciplines would necessarily converge. The project consists of 3 phases: a chemical phase, a mathematical phase, and eventually an interdisciplinary phase, where the 2 distinct concepts merge through a single learning process. The project was run in a class of secondary school students, 12-aged, following a methodological approach. Each concept was built gradually, with great attention to the use of language, so that the teaching message would be most effective. The teacher was able to implement a didactic contract while developing a learning process based on discussing and sharing with the class problem-solving procedures. All the activities have been approached with a lab-style method and with a student's active role in testing each single theory proposed in the running of the project. All the activities were recorded on individual cards for each student, and the results were discussed first within small groups and then with the entire class. Discussions with the entire class always resulted in commonly shared definitions. Through simple lab tests, the mathematical phase of the project starts investigating some solid substances when immersed in water. Some are soluble, some others are insoluble. Some are white, some others have different colors. This leads to a first possible definition of a solid soluble substance, based on the different look of the liquid obtained from its dissolution in a beaker. Next comes the investigation to verify if after the experiment the solution contains both the solute and the solvent. This is done by comparing the apparently similar liquid contained in 3 different beakers, one containing just water, another one water and salt, the last one water and sugar. Surprisingly, the majority of the students believe that a given quantity of solvent can dissolve unlimited quantity of solute. This belief must be destroyed through a clarifying lab activity. To verify their theory, the students agree to run a class-shared experimental test, after which they discover that indeed there is a limit to the solubility of the different solid substances that have been used. During this phase, a few definitions are clearly understood, such as saturated solution, precipitate, and limited to solubility. Each definition works as a conceptual synthesis for the activity that was completed and is formulated in a language that is consistent to the student's vocabulary. Meanwhile, the concept of ratio and proportionality is being built through a number of stimulating activities, useful also to build a multipurpose model. The concept of ratio is presented as a means of comparison for homogeneous quantities by introducing the concept of a scale factor while comparing the ingredients of a recipe for a variable number of people. Calculating the quantity of nutrients in a given type of food and comparing the geometrical measure of a side of a square and its diagonal are further teaching topics proposed to the class. This type of approach leads then to consider the different ways in which the ratio can be expressed as a decimal number, a fraction, a percentage. Each possible option to express a numerical ratio can also be verified on a computer spreadsheet. These notions can be most effectively represented on a chart by using a Cartesian plane of coordinates to show how the ratio y over x remains constant for both the real measurements and the model ones. The concept of concentration is introduced moving from the mathematical to the chemical phase. To this end, the students are given an individual card where they have to calculate the quantity of solvent and solute required to prepare a solution as wet as the schoolmate's one, using different quantity of water and sugar. Many students suggest using the notion of ratio and manage to calculate correctly the quantity required to prepare equally sweet solutions. However, I decided we should return to the lab to be able to better build the concept of a chemical concentration. The students are presented with a number of similar copper sulfate solutions, showing a scale of different color depth. After debating the situation with the class, the majority of the students come to the conclusion that the deeper color solution is the one containing the largest quantity of copper sulfate or solute. However, such a conclusion comes to question when comparing some of the different column solutions with the respective quantity of solute as shown on a level. The students can easily understand that their early conclusion conflicts with what they can see and start thinking that the solution color may depend not only on the solute quantity but also on the solvent quantity taken in consideration together. Eventually, the students reach a conclusion using the mathematical concept of ratio as a means to safely determine how deep the color of a solution is. This then leads to the definition of concentration as a ratio between grams of solute over grams of solvent. Once again, using a Cartesian system of coordinates to represent the mathematical relation between the quantity of solute and solvent in the free virtual solutions helps confirming how graphics, algebra, and spoken language can interconnect when describing a numerical ratio. In conclusion, I would like to emphasize the importance of both lab experience and the students' active role for attaining the most effective teaching results in terms of general knowledge, students' involvement, and the common building of definitions. At this point, I would like to share with you a comment from one of my students who, on reviewing the class project, said that he had felt like a puzzle with one missing piece until he could complete the work together with his classmates. At the end of my work, I would like to thank you for your attention, and a special thanks to all people helping me to prepare this project. Aldo Borsese, Marcella Mascarino, Irene Parachino, who helped me with chemistry and teaching communication, to Carlo D'Apueto for his help with the mathematical part of this project, and to Mara Polarolo and Giovanni Cecchinato for their help with the English translation. Finally, I'd like to thank also my school principal, Anna Bianchi, who constantly promotes innovation in teaching methodology for the best educational results of our students.